Good evening. Today we are going to continue our discussion on spherical polar coordinates and solve some example problems. So far what we have done is we were looking at how to solve the Laplace equation, which is del squared phi is equal to 0, which is valid when there is no charge density. Because when charge density is 0, you have del squared phi is equal to 0, and that's what we were looking at. And we chose a subset of solutions because we are assured of a unique solution through the uniqueness theorem in spherical polar coordinates or any other coordinate system. We can choose solutions that could be separated into forms like this. And in fact, we did this in the last lecture, and we separated out equations that depended only on r, only on theta, and only on phi. And we found that the solutions for these look like AL r to the power L by BL r plus 1. And this, we saw that the functions were Legendre polynomials where x is equal to cosine theta. And these also depend upon m, where m is the exponent here in the solutions to the phi, e to the power im phi. And we saw that if there is phi symmetry, then m is an integer, and m goes from minus L to plus L, and L is an integer. This is what we have seen from solving the differential equations. And then we also saw a very specific property of the Legendre polynomials, that was PL of x is equal to PL of minus x, that is, it is even if L is even, and PL of x is equal to minus PL of minus x, or it is odd if L is odd. And we saw that essentially when you expand these PLs, these are polynomials. So recall that these polynomials form a complete set. That means you can express any function as a sum of these polynomials. So you can describe any function as a series, just like you do in the case of Fourier series. You could also use polynomials, which are a complete set, and they become a complete set because we have seen another specific property of the Legendre polynomials in the last lecture, that they're orthogonal. So that means that if I have two different Legendre polynomials with a different index here, L and L prime, and I do the integration over dx. So x is equal to cosine theta, so the integral goes from minus 1 to plus 1, which are the limits for cosine theta, or in terms of theta, we could write this as d theta sine theta, PL cosine theta, PL prime cosine theta. We saw that this is equal to 0 if L is not equal to L prime, and is equal to 2 by 2L plus 1 if L is equal to L prime. So that's what we call as orthogonal. That means there is no dependence here, that these are independent. PL cannot be expressed in terms of PL prime in any way. So they're independent. So when you integrate them, they give you 0. This is like similar to saying, like, in an analogical sense, when you have x dot y, right? X dot y is 0 because y cannot be expressed in terms of x. There is no projection of y along x. So that's what we are saying here, that if you have PL and PL prime, they are like x and y in an analogical way, in that they are completely independent, like x and y. Like how y cannot be expressed in terms of x, similarly we are saying that PL prime cannot be expressed in terms of PL. And if L is equal to L prime, then they are essentially the same function. So the integral doesn't cancel out, and you get 2 by 2L plus 1. So we call this property of the integral being 0 when L is equal to L prime, not equal to L prime as orthogonality. So equipped with this, we also defined another new function called the spherical harmonics. And at the core of it, the spherical harmonics, which are denoted by YLM theta phi, are essentially a product of the Legendre polynomials PLM of cosine theta and the azimuthal solution e to the power im phi. And we added some factors here like 2l plus 1 by 4 pi L minus m factorial by L plus m factorial. And these factors were added in so that when we write the orthogonality for spherical harmonics, that is, if I write YLM theta phi and YL prime m prime theta phi sine theta d theta d phi, if I do that integral, then we would like to write that as delta LL prime delta MM prime. So to do that, we add in those factors so that, for example, when you look at this 2 by 2L plus 1, if I were to have a 2L plus 1 by 2 already here as a factor in defining the Legendre polynomials, then I would have essentially gotten 1. So then I can represent this function with a Kronecker delta. So that's the idea there. So to do that, we are pre-multiplying with this factor so that when we do the integral, unlike the Legendre polynomials which give you some number, here it is normalized to give you 1. So you can represent it with a Kronecker delta like this. So in general, if there is a spherical system, if we have some spherical system, then we know in general I can write phi of r theta phi as sigma L is equal to 0 to infinity AL r to the power L plus BL by r plus 1 into PLM cosine theta e to the power im phi. So this is the r part, this is the theta part, and this is the phi part. And we are summing over L is equal to 0 to infinity because what we are saying is that in general, any general solution can be expressed as a sum of these functions because these functions are independent. These are just like how you can express if you have x, y, z coordinates. For example, if I have x, y, and z like this, these form a complete set, right? And that if I do x dot y or x dot z, I get 0, right? And the same thing applies for y and z. And then I can express any vector. For example, if I pick some point here, any vector, I can express it as some ax times x plus ay times y plus az times z. So if I have an orthogonal set of complete set of coordinates like x, y, z, I can express any vector as a sum of x, y, z. In a very similar way, in an analogical way, not in a direct way, in an analogical way, what we are doing here is that we have these Legendre polynomials and these functions that are independent, that have this orthogonality like how we have seen. So then we're essentially saying that any general solution to phi can be expressed as a sum of these. So this is a general solution. So we have come up with a general solution. If we want a specific solution, we need to apply boundary conditions. So if you apply boundary conditions that are specific to our problem, then from this general solution we get a specific solution. So what does this mean? This means that in general we are writing this as a sum with some coefficients. So we are writing it as a linear combination. So we are writing it like this, so on and so forth. But we don't know really what these coefficients are in the general solution. So when we apply boundary conditions, for example, if I have the condition that phi as r goes to infinity, phi of R should go to 0, right? So in such conditions, you can see that you cannot have AL, because if AL is not equal to 0, then this term R to the power L would diverge as R is going to infinity, so you wouldn't have a good solution for your phi. It doesn't satisfy the boundary condition that phi should go to 0 as R goes to infinity. So if there is a boundary condition that is specific to the problem, we apply that boundary condition here, and then accordingly set the coefficients either to 0 or find out what the coefficients are. So the specific solution, essentially applying boundary conditions, gives us what these AL and BL are specific to that problem. So this is what we have done so far, so that we got a general solution, and now we're going to see with examples how we can apply boundary conditions and get a specific solution. So first we'll start with example 3.6 in Griffiths. So here what we are given is we have a sphere of radius r, and we are given that the potential on this surface is specified by a function, and this function depends upon theta. So the potential on the surface of the sphere is given to us as the boundary condition here. So essentially what we are being told is that phi of r is equal to r theta, and phi is equal to phi 0 of theta. This is the boundary condition that we're being provided, right? So in general, if you just have a sphere without, let's ignore this boundary condition for now. Let's say you have a spherical conductor, and then essentially your problem is spherically symmetric. It depends only on r, correct? But here we are given an extra condition that depends upon theta. So we are specifying potential as a function of theta. So our problem is not completely just dependent on r, it is dependent on r and theta. But with respect to phi, it is still symmetric because the boundary condition depends only on theta. It is the same for all phi. So we can easily set m is equal to 0, that is, remove the phi part. So our potential is essentially just a function of r and theta. So then we can write the general solution as L is equal to 0 to infinity AL RL plus BL by RL plus 1, and PL M is equal to 0 cosine theta. So now here we have different parts. We have inside and we have outside the sphere. And the boundary condition is given by this. This is the boundary condition. So if I look inside, that is r less than r, then as r goes to 0, this phi should not diverge. It should not go to infinity as r goes to 0 inside the sphere. So as r goes to 0, you cannot have the potential diverge. So that would mean that inside I will have to set BL to be equal to 0. So inside we have BL equal to 0. So similarly, if I look outside as r goes to infinity, phi should go to 0. So then clearly we cannot have an AL term, because as r goes to infinity this term would diverge. So outside AL is equal to 0. So now then we can look at what the potential should be on the surface. So if I look at the potential inside, that would look like L is equal to 0 to infinity AL r to the power L PL of cosine theta, because we set BL equal to 0. And if I look at the potential outside, then that would look like sigma L is equal to 0 to infinity BL by R to the L plus 1 PL of cosine theta. Right? And then these two things have to be equal at the surface. At R is equal to R, we have the boundary condition. So we figure out the potential outside and inside. And then now we have another extra boundary condition. So the extra boundary condition is that phi at R is equal to R and theta is given to be some phi 0 of theta. So if I look at phi inside at R is equal to R and theta, I have sigma L is equal to 0 to infinity AL capital R to the power L, because we're setting R is equal to R, PL cosine theta. So this we're given is equal to phi 0 of theta. So now it's quite straightforward to figure out the what should be the value of each AL from here. So all that we need to do is we are going to multiply this entire equation, multiply with sine theta PM of cosine theta, where M is not equal to L, or we can call it PL prime, because that's the notation we used, and I don't want you to get confused with this M and M with respect to the azimuthal part. So we'll just call it L prime. So we're going to multiply this entire equation with sine theta PL prime cosine theta. So then we would have here L is equal to 0 to infinity AL R to the power L PL of cosine theta, PL prime of cosine theta, and sine theta. We're multiplying each term with this. And on the right hand side we would have phi 0 of theta, PL prime of cosine theta, sine theta. We just multiplied with this term. That's all we did. And then we can integrate this, integrate both sides from 0 to pi. Right? And then you would see that this part is independent of theta really, so I can carry the integral over. So I would have L is equal to 0 to infinity AL R to the power L PL cosine theta, PL prime cosine theta, PL prime cosine theta, sine theta d theta, and the same thing here, 0 to pi phi 0 theta, PL prime cosine theta, sine theta d theta. But recall that we have looked at the orthogonal relationships between PL and PL prime. We saw this is very similar in an analogical way to saying x dot y is equal to 0. So this PL prime would be 0 unless L is equal to L prime, and then we can write this part. So I'm going to rewrite that. So we have L is equal to 0 to infinity AL RL integral PL of cosine theta, PL prime cosine theta, sine theta d theta is equal to integral of phi 0 of theta, PL prime cosine theta, sine theta d theta. And from the orthogonal relationships, this is equal to 2 by 2L plus 1 delta LL prime. So then I can write this left hand side as L is equal to 0 to infinity AL R to the power L 2 by 2L plus 1 delta LL prime. So this is a series of terms that are being summed over. So L goes from 0, 1, 2, so on and so forth. But here we have a term L prime, delta L prime. That means this term is picking out one single term L prime from that entire series. From this entire series, by multiplying with Kronecker delta, we're picking out one single term. And that one single term is AL prime r to the power L prime 2 by 2L prime plus 1. And this is equal to phi 0 theta PL prime cosine theta sine theta d theta. Right? So then the term AL prime, that the single term that we picked out, would be 2L prime plus 1 by 2 to the power RL prime integral of phi 0 theta PL prime cosine theta sine theta d theta. So this L prime here is really a dummy index, in that we're saying A of L prime is whatever this L prime is, you just plug that number in here, right? So I could as well write it as just L instead of L prime, so it just looks nicer. So then we would have AL figured out. So using the third boundary condition, the first boundary condition was R going to 0, the second was R going to infinity, and the third was we specified the function to be phi 0 of theta, and that is given to us. This is the boundary condition. We know the Legendre polynomial, and we simply do the integral to get this term AL. Now we could do the same thing for outside, right? Here we started with the inside potential while setting the boundary condition, but even the outside potential should reach the same phi 0 of theta when you set R is equal to R. So we could do the same thing for phi outside. So phi outside, R is equal to R, theta would be sigma L is equal to 0 to infinity, BL by R minus plus 1 PL cosine theta, right? So then this, we set this equal to phi 0 of theta, and in the same way that we did for the last term, we're going to do a similar integral here, and then if we integrate with PL prime cosine theta sine theta d theta. So we are, if I call this equation star, that's what we are doing to star, that we're taking this equation star and multiplying it all throughout with PL prime cosine theta sine theta d theta, and then integrate over 0 to pi like we did the last time, so we can use the orthogonal relationships for these PLs. And then I can simply write similarly, just like how I wrote AL here, I could write an expression for BL, and BL would be 2L plus 1 by 2 R to the power L plus 1 0 to pi d theta sine theta phi 0 of theta. This is the function that is provided to us, and PL of cosine theta. So we figured out BL. So then we can now write the total potential. So our goal, we were given our problem, original problem was that we have a sphere of radius r, and we were provided the surface potential as phi is equal to phi at r is equal to r, and theta is equal to phi 0 of theta. Then we figured out that BL has to be set 0 inside, and we figured out what AL is inside. So we can write the phi inside as sigma L is equal to 0 to infinity AL r to the power L PL cosine theta, and we figured out what these ALs are. We saw that these ALs are nothing but 2L plus 1 by 2 times r to the power L integral 0 to pi d theta sine theta, whatever is the potential on the surface, phi 0 of theta, times PL of cosine theta, right? This is inside. And similarly outside, we figured out that BL outside is not equal to 0 and AL outside is equal to 0, and so we expressed phi outside as sigma L is equal to 0 to infinity BL divided by RL plus 1 PL cosine theta, and we also figured out these BLs using a similar method that we did for AL, and so BL is equal to 2L plus 1 by 2 times R to the power L plus 1 0 to pi d theta sine theta phi 0 of theta PL cosine theta. So notice that we now have a very specific solution. This is specific because these A's depend upon the radius of the sphere, they depend upon the surface potential that you are giving, and so these are giving you the specific solutions to this specific problem. So in general, we started with a general solution and we applied the boundary conditions. We started with azimuthal symmetry, set M is equal to 0 there, and following that we used the boundary condition phi 0 of theta to find out AL and BL and come up with a solution that is specific to this problem. So now let's see how we could solve this problem instead of the potential on the surface if we are given a different boundary condition. So we have exactly the same problem, but instead of defining the potential, I can define the charge density. That would be a different boundary condition, right? So how would we solve this same problem if instead the charge density on the surface was specified? So that's very quick and straightforward to see. Again, we have the same exact problem set up. The only difference is that we are given sigma of theta, the charge density. So still we have phi inside of r theta. It is still the same thing applies, that it is L is equal to 0 to infinity AL r to the power L PL cosine theta, and phi outside of r theta is sigma L is equal to 0 to infinity BL by R plus 1 PL cosine theta, right? And we know that as you go from inside to outside, because the charge density is specified here, we know that the function phi itself is continuous. Phi itself is continuous. So if I do phi out at R is equal to R, that should be equal to phi in at R is equal to R, right? So that means sigma L is equal to 0 to infinity AL capital R to the power L PL of cosine theta is equal to sigma L is equal to 0 to infinity BL by RL plus 1 PL cosine theta, right? So these two terms are equal at R is equal to R. So then we can see a relationship between these two terms. We can see a relationship there. So we could write AL to the power R to the power L is equal to BL R to the power L plus 1. These have to be equal to each term because we have seen that these PLs are independent of each other, and because these PL cosine thetas are independent of each other, that is, for example, P1 of cosine theta cannot be expressed as P2 of cosine theta. It cannot be expressed in terms of any other function like x and y. And so each of these terms have to be equal, each of these coefficients would have to be equal for this overall equality to work out. So then we have AL to the power RL is equal to BL by R plus 1, or I can write BL as AL times R to the power L times R to the power L plus 1, or AL R to the power 2L plus 1, right? So that's the thing that we get by just equating, by noting that our phi is continuous. So we're equating the outside and inside potentials at R is equal to R. And then we are given the charge density here. If you recall, the boundary condition we derived for the charge density was minus dou phi out by dou r plus dou phi in by dou r at r is equal to r should be equal to 4 pi k sigma, right? Or this is sigma by epsilon naught. So now we can apply that here. So we have minus dou phi out by dou r plus dou phi in by dou r is equal to sigma by epsilon naught, and we have phi out to be equal to BL by r plus 1. I am not writing the summation explicitly, but assume that L is going from 0 to infinity, right? So if I do dou phi by dou r for out, I would have minus L plus 1 BL by BL times r to the power minus L minus 1 PL cosine theta, or I would have minus of L plus 1 BL r minus L minus 2 PL cosine theta, or that is minus L plus 1 BL by r to the power minus of L plus 2 PL of cosine theta. And I need a negative sign here, so this negative sign would go away. So here I would get L plus 1 times BL by r to the power minus L plus 2 PL of cosine theta, right? We are doing only with respect to r here, so it's not dependent. This PL of cosine theta is just simply a constant there. So then for inside, phi inside, again we are not writing the summation explicitly, but it is implied, PL of cosine theta. Then dou phi in by dou r would be equal to L times AL r to the power L minus 1 PL of cosine theta, and we could plug that in here, L AL r to the power L minus 1 PL of cosine theta is equal to sigma by epsilon naught. Now here in this relationship, we know what should be the relationship between AL and BL, because we derived it on the previous slide. So we know that BL should be equal to AL of this much. So I can write then, instead of BL, if I plug in AL times r to the power 2L plus 1, right? Then here I have minus L plus 2, so I would get AL r to the power 2L plus 1 this should be r to the power plus L plus 2, sorry. This should be plus L plus 2 because that minus is the reciprocal, so I messed up there. Probably you noticed my mistake before I did. AL times r to the power 2L plus 1 minus of L plus 2, so we would have AL r to the power 2L, so we would have r 2L minus L is L, and minus 2 plus 1 is minus 1. So we ended up having the same coefficient like the second term. So we would have something that looks like L plus 1 AL times r to the power L minus 1 PL of cosine theta here. And here we have the next term is simply plus L times AL RL minus PL of cosine theta. So then you can pull out AL times RL minus 1 as a constant, and recall that this is all at r is equal to r. This is the boundary condition. This is at r is equal to r is equal to r. So then we can write this entire condition only in terms of AL. So essentially what we did was we applied the boundary condition minus dou phi out by dou r plus dou phi in by dou r at r is equal to sigma of theta by epsilon naught. We took the derivatives, we plugged in R is equal to R, and we used the relationship from phi being continuous, the potential is continuous. From there we got this relationship of R 2L plus 1. So then from here we essentially got sigma L is equal to 0 to infinity 2L plus 1 capital R to L to the power minus 1 AL PL of cosine theta is equal to sigma of theta by epsilon naught. So now it's quite straightforward to figure out what AL should be here, just like how we figured out AL in the previous case when we had the boundary condition on potential instead of charge. We could do the same trick. So we multiply with sine theta PL prime cosine theta and do the integral. And if we do that for this specific condition, if you are given sigma of theta, then you can figure out AL to be equal to something like 1 over 2 epsilon naught R to the power L minus 1 0 to pi d theta sine theta sigma of theta PL of cosine theta. So this would be specific to the problem. So in the previous example, when we specified phi 0 of theta, that phi 0 of theta was what was featuring in the integral. Here, instead, we are specifying the charge density, so that's what is featuring in the integral. So based on the boundary condition from the general solution, by applying boundary conditions, you figure out the coefficients like AL and BL in this case, and our solution. And you are assured that this solution is unique because you have applied these specific boundary conditions. That is what the uniqueness theorem says, right? So with this, we will stop how to solve separation of variable problems, and then look into a little bit into image charge method, and then finally recall what we did in multipole expansion, and then move on to the next chapter of electric fields and materials. Thank you.